Okay, now let's look at control charts for attributes as opposed to control chart for variables. Remember, variable control charts, they always go as a pair. For each variable, you will have two charts, X bar chart and R chart. And a particular production process can have many variables. And for each variable, you will have those pairs of charts. Whereas attribute charts are about the outcome of the production process, the product that comes out finally. And then you look at the product and then see whether it is defective or not defective. And there are two different charts of this type, and you will usually choose one of them. You either do the P chart or the C chart. P chart is for percent defective. So if you have a production process in which parts come out, you take a sample of say 50 units and then say what proportion of that sample is defective. So you have 50, two of them are defective, so defective is 4%. Is that good or bad? Okay. Then you need to, you use the same procedure like before. At the stage of developing the control limits, you would take frequent samples, okay, repeatedly every 10 minutes, 15 minutes or whatever, and then make the computations and then check the chart, plot the values and check the chart against the run tests, that 5 different run tests that we talked about, and see whether the control charts are in control. In other words, there are only natural variability. Okay. So that would be proportion chart or P chart. With a C chart, and the C stands for count, and that would be number of defectives. Say like you take a part and then see how many defects there are. So you take a document, see how many typos are there. That kind of stuff. Or you take a carpet of 100-yard carpet, how many defects there are in the carpet. Okay. Take a cable and how many how many blemishes there are in the cable or things like that. So count as opposed to proportion. So the formulas are fairly straightforward, very straightforward, I would say. And the key is in determining which chart is appropriate when. Okay, so P chart formula, okay, is similar to the one that we saw in the beginning. So you have P bar plus or minus Z sigma sub P. Okay, and the sigma sub P is computed using this formula. And Z here, like what we've seen before, it can be either 3 or 2. If it is 99.7% interval that we are after, you'll use a Z of 3. If it is 95.5, you'll use a Z of 2. Okay, so here is an example. So we have 20 samples. In each sample, we had 100 database entries from each clerk. How many errors there were? Okay, the first clerk, out of 100, there were 6 errors. So fraction defective is 6 over 100. Okay, you calculate that for each of them. Okay, and then if you sum all these errors, okay, total of 80 errors, 20 clerks, 100 each, so 2000 entries, there are 80 errors. So if you divide 80 by 2000, then you get P bar. You can also get that by simply averaging these fraction defectives. That will also give you P bar. And then plug that into this formula, you get sigma hat sub P. Okay. And again, you have to be very careful, distinguish between number of samples and sample size. Sample size is the number of observations in one sample as opposed to how many samples there are. So here there are 20 samples, each with 100 observations. So N is 100, and then you plug it in and calculate it out. And remember, because sigma sub P is not in our, it's based on the fractions, it's possible that the lower control limit may compute out to be a negative number, and that's not possible. Proportion cannot be negative. So if this number calculates out to be a negative number, you have to round it up to 0. You can't leave it as negative whatever. Okay, that would be wrong. So you have to make sure that you don't leave negative values as control limits. Okay, and then you plot the lower control limit, upper control limit, and the midpoint. And here you see this one point lies outside the. Now all the 5 run tests will apply here as well, but here the one that applies here is the one that's outside. So here again, see, you can see there is a run of 5 right here. So here also a run of 5. So there's more than one reason why this process will be considered not in control. Okay, let's look at the problem here in Excel. So we have the 20 employees, and here are the errors from the 20 employees. Okay, so the fraction defective is that divided by n. N should be here, and press F4. Okay, let's enter 100 there. Okay, and then copy that down. Okay, format properly. Let's put the bottom border back. So total errors is at 80. We already knew that, right? So total entries is there are 20 samples, each with 100 observations. Okay. So P bar is that divided by that. Yeah. And you can also find P bar by simply averaging this. That also will give you the same answer. Okay. Then the standard error of P is square root of P bar times 1 minus P bar divided by sample size, not number of samples, sample size. Okay, so that gives us the sigma value, and then for 99.7% Z is 3, so 3 times sigma sub P will give you the sampling error or margin of error, and then we go P bar minus the sampling error will give you the lower control limit, and P bar plus the sampling error will give you the upper control limit. Okay, now of course this cannot be negative, so for lower control limit the formula you should use is max of that or 0. So if that happens to be minus a negative value, then you'll have 0. So now let's set up the plot. So we need the LCL, lower control limit, and then we want P bar, and then the upper control limit, right? So then you want that to be repeated for each of the 20 cases. So set that equal to the previous cell, and then if you copy down, okay, so then let's plot these horizontal lines first. Okay, so we have the 3 lines. Okay. Add P, and the series values are the fractions. Okay, so now we have the plot, and you see that there is a point that falls outside, and here that one is not showing up correctly, and that's because the P bar font is not good, so it's not appearing properly. So let me spell it out as P bar and also add chart title. So that would be P chart.